we all know the law for conservation of energy that tells us energy cannot be created or destroyed. It can only be changed from one form into another. So if I say I am using energy, it's actually incorrect. I must say I am converting. You can't use energy, you convert it. Okay, from one form into another. Unfortunately, with each conversion of energy, some energy is always converted into a useless form, one that the system can't use. It's usually in the form of heat and sound. Sometimes a little bit of light, but usually when there is light, we use the light in the dark when it's dark. Okay, so the light isn't always a waste of energy. All right, but sound and heat is the most common way in which the energy is lost to the system. All right, so energy cannot be created or destroyed. It can only be changed from one form into another. Energy conversions are not 100% efficient. In chemical reactions, we need energy to break bonds, all right? And chemical reactions release energy when bonds are formed. So when we write a chemical equation, usually if I have hydrogen plus nitrogen and it forms ammonia, for example, we can balance it there, then on the reagent side, we have to break the chemical bonds between the diatomic molecules. There's a diatomic molecule and there's a diatomic molecule to get separate atoms. All right. So usually on the reagent side, we have bond breaking. And here, on the product side, we have made new bonds. Nitrogen and hydrogen now stick onto each other. Here we usually have bond making. Now, if more energy is used by bond breaking than given off by bond making, we have an endothermic reaction. If more energy is given off during bond making than breaking, we have an exothermic reaction. Here we have the graph. This one is endothermic, all right? Can you see here the reactants? More energy required to break the bonds than the energy that is given off during bond making. Do you see that? That is an endothermic reaction. We call this energy hump, this bump. We refer to it as activation energy. All right, this is not new. You've done this previously. Okay. Photosynthesis, for example, is endothermic. If I take a plant and I pack it inside my dark cupboard and I close the door, no photosynthesis occurs because it requires more energy to break the bonds between the carbon dioxide and water vapor to make than what is given off during the bond making to form the carbohydrate plus the oxygen. So if there's no sunlight, there's no photosynthesis. Activation energy is the energy required by the particles that will enable them to collide with enough force so as to cause a reaction. Once the particles have broken apart, now the bonds have been broken, these particles have got energy, so they move. And they will bump into each other. Now when they bump into each other like that, with a large enough force, bang, then new chemical bonds can form. So many of these particles just bump and bounce off, all right, and then at a certain point, they can form a chemical bond if there is enough energy. That is the activation energy. Here we have an exothermic reaction. Exothermic reactions give off energy. Why? Because the energy required to break the bonds is much less than the energy given off during bond making. Yeah. All right. So it is exothermic. Most of the chemical reactions that you will come into contact will be exothermic, okay? Because usually the product is more stable than the reagents. In an endothermic reaction, the product is actually unstable. What happens to a plant if it stops photosynthesizing and it dies? No, it decomposes. It forms methane gas, among other things. Do you understand? Okay, so usually the product of an endothermic reaction, because it lies at a higher state than the reagents, it's usually more unstable. And in nature, everything tends to go to the lowest energy state possible. It's a law of nature. So exothermic reactions, the products are more stable than the reagents. Okay, so magnesium metal can burn bright white light. It forms magnesium oxide. Magnesium oxide is very stable. In actual fact, it's very difficult to get the magnesium from the magnesium oxide again, because you have to break that bond and it requires a lot of energy. Okay, what is a fuel? Store of chemical potential energy. Where in a fuel is the energy stored? Within the chemical bonds. In other words, between the shared electrons is where the energy lies. All right. We get two types of fuels, just basic. There are different ways of classifying them, but in general, renewable and non-renewable. When is a fuel renewable? Okay, when they don't run out. In other words, it is a fuel that can be replaced within a reasonable time period. For example, I can use wood for a fire to make a braai, but I plant trees. Okay? The trees and the bushes grow in a reasonable amount of time. The people who make paper, they have plantations of trees, these pine trees that they make the paper from. Okay? So their paper is renewable because they plant so that they can, after, I don't know how many years they grow, 5 years, 6 years maybe, they can harvest the wood. All right? And then they replant again. Okay, so renewable and non-renewable. Renewable fuels can be replaced in a short period of time or a reasonable period of time. Non-renewable are fuels that take very long to form. Now, at this point, we classify the fossil fuels, coal, petrol, diesel, as being non-renewable. Although, if I plant sunflowers, and I harvest the sunflower seeds, and I use the oil from the sunflower seeds to produce petrol or diesel, then my diesel, is it renewable or non-renewable? It is renewable. Okay, so you must go and have a look at the situation. All right, there are some countries that plant sugar beets. From that, the sugar, they get ethanol, and they use ethanol as a fuel. That is renewable. But most of the ethanol we use come from fossil fuels. So it is non-renewable. Up in the north where they harvest wood, why has the government stopped the harvesting of wood? Or say that they've stopped it? Why? Yes, nobody's planting any trees. And the trees that they are harvesting are hardwood trees. They grow very slowly. It takes more than a lifetime to replace a tree like that. So that wood would be non-renewable. But if you have a leather couch at home, the wood on the inside of that leather couch is 99% sure pine, which is renewable. If you have a sitting room set and it's made from sleeper wood, do you know what I'm talking about? Okay? It's non-renewable. Why? It's a wood that is hard. It's like iron. It's so hard. It is a very slow-growing tree. You don't get them anymore. All right? And they used them when they built railway lines. Was the hardest material available those days. Nowadays, we can use concrete, reinforced concrete. Okay, but those sleepers, as they dig up the old railway lines, they pull out those wooden sleepers and they sell them. They're very, very expensive because it's just not available anymore. No? Okay, so in that case, the wood is non-renewable. So whether the fuel is renewable or non-renewable, it sort of depends a little bit on the situation. But in general, fossil fuels are non-renewable. sunlight, wind energy, water energy, etc., is renewable. Yeah. Okay, so solar, wind, water, and in general, fossil fuels are non-renewable. Futuristic fuel. Why is hydrogen a futuristic fuel? Why is it actually a brilliant fuel? Well, hydrogen reacts with oxygen and it forms water. Yes. Okay. Water is an exceptional fuel. When hydrogen burns with oxygen, it burns with a very hot flame, so there's a lot of energy being given off. The product is water, which actually is quite easy to break up with electricity into hydrogen and oxygen. So I could have a closed system. There where the exhaust blows out the gases into the atmosphere, we have a pipe going to a tank in which it causes the hydrogen, the water to be broken up using a little bit of electricity generated from the movement of the car. You would have an endless supply of fuel. Why? They have done it. But why? What is the problem with hydrogen here on Earth? Why can they use it in outer space? It's rocket fuel in outer space. Why? There is no oxygen. Here on Earth, if I have a hydrogen tank and it springs a leak, and it leaks the hydrogen, what happened to the Hindenburg airship? It exploded when it came to dock because the hydrogen balloon leaked some hydrogen. And at the docking, there was a spark, and when hydrogen is mixed with oxygen, it forms an incredibly explosive mixture, which is very dangerous. Okay, very difficult to control also. And that is why, at this point, we haven't used water as a futuristic fuel, but you don't need to make water. Take an oxygen tank and a hydrogen tank and add them together and light the hydrogen. Yes, it'll make droplets of water. Now, because hydrogen is difficult to use, okay, we go and look at other sources of energy. Now, if I want to walk around in the dark, I need a flashlight. So in the flashlight, I need batteries. And if you've got a younger brother or sister, he's probably played around with a torch at some point and the batteries are flat. Okay, and we have to replace them, and they're expensive. Okay, how do these cells work? Now, the difference between a cell and a battery, a cell is one. A battery is two or more cells put into a container. All right. The simplest cell that we can set up, or one of the simplest cells that we can set up in a laboratory, is just simply a solution of, well, any substance that will have ions in it, so dilute sulfuric acid or a salt solution, sodium hydroxide, one of those, etc. Now, with the ionic solution, we have a copper electrode. There is the copper electrode. And we have a zinc electrode. Now, we've done a chapter on metals. Which one's more reactive? Zinc is more reactive than copper. All right. So, when we go and connect these two electrodes with a copper wire, these two electrodes, they start fighting over electrons. And the more reactive one loses his temper first and he loses his electrons. The less reactive one takes up the electrons. So, we can stick a lamp or a bulb in on the circuit and our bulb should light. What happens at these electrodes? Because after a while, what happens to my battery? It goes flat. Why does it go flat? Well, the chemicals have been used up. All right, and they aren't, it's not a reversible reaction. If I have a rechargeable battery or cell, then I can reverse the flow of charge through it, and to a certain extent reverse the chemical reaction. All right, but it is also not endless because the chemical materials, they eventually deteriorate. Okay, and at a certain point it can't hold the charge. Now what happens is, over here, because these two electrodes fight over the electrons, the zinc electrode tends to lose its electrons. Okay? So the electrons go moving through the circuit. But the moment I have a zinc ion, it goes into solution. So what's going to happen to the zinc rod? It's eventually going to disappear. All right. If my cell is set up like this, at a certain point, if enough zinc goes into solution over here, the solution becomes so positive around this rod that it doesn't allow the electrons to move over towards the copper rod. Okay, and then the cell is flat, it doesn't want to work anymore. Now because we have a solution over here, in the solution we have sulfate ions, we have hydrogen ions, because it's diluted in water. We find that over here on this electrode, okay, the hydrogen in the water, the ions in the solution, will gain an electron because these electrons are there. They can't go into solution. So when a hydrogen bumps into that electrode, what's it going to do? It's going to gain an electron. All right? And we will get the formation of hydrogen gas. And that's the little bubbles that they show over here. Little bubbles of gas can eventually escape. We get the formation of some hydrogen at the other electrode. All right. So just simply the theory, the two metals compete for electrons. We find that the more reactive one will lose its electrons to the less reactive one. The less reactive one doesn't want to react, so it holds on to its electrons. All right. The electrons travel then from the zinc electrode to the copper electrode. The zinc electrode forms zinc ions, which goes into solution. It will dissolve. So the zinc rod is going to disappear eventually. The batteries, if you buy torch cells and you put them in the torch and they flat and you just leave them inside there, what happens? Acid leaks out because the zinc casing, because in the torch cells we have a zinc casing, all right, and we have a carbon electrode in it, inside a cover. Oh. So when the zinc casing is used up, the acid can leak out and it causes corrosion of the contacts in the torch or wherever the device. No. Okay, so the zinc will dissolve because they go into solution. The less reactive metal will always, in this case, remember we've not connected it up onto a battery. There's not a battery with a positive and a negative pole. But when we have a cell like this, we talk about an electrochemical cell. We say the less reactive metal will be the positive rod. Where on a torch cell is the positive and where's the negative? The zinc casing forms the negative pole. We have a carbon electrode in here which is unreactive. That forms the positive pole. Okay, so just remember, try and it becomes confusing, okay? But the less reactive metal is the one that will be the positive pole. Okay, so the copper electrode in this case that I have here, the potential would be the positive pole. So if I went back to this diagram, the copper electrode would be positive and the zinc electrode would be the negative pole. All right. Potential difference that is produced between these two metals depends on a couple of factors. The one factor is the reactivity difference. If the reactivity difference is more, it will produce a greater potential difference. Okay, it's also got a little bit to do with the concentration of the solution around it. But we don't go into standard cells in our syllabus. It doesn't, so you don't need to do that. The potential difference then depends on the difference in reactivity between the metals. The greater the difference, the greater the potential difference produced. Now, your syllabus refers to a lead acid cell. Now, lead acid cell is the car battery. It's got lead plates and there's sulfuric acid in it. Now, they say you must know basically what it works. Now, the working is fairly complicated and your syllabus doesn't exactly give all the detail. All right, so those of you who are struggling with them, I don't say don't learn it, but I wouldn't be too bothered about it. In the 15 years that we've had this syllabus, they've never asked anything on it. Okay. So, but what basically happens is in the lead acid cell in a car battery, we have 6 sets of cells to make the battery. Okay, each set is a 2-volt source, and the battery altogether makes 12 volts. The electrolytic solution, that is the liquid in which the electrodes are found, is sulfuric acid. It's dissolved in water, so the acid is ionized. It's got sulfate ions, and it consists of hydrogen ions. When you charge the battery, then you connect a power supply to it. You've got a positive connection and a negative connection. So the positive connection is the anode, and the negative connection is the cathode. Okay? And we find then that specific chemical reactions occur. They say when the external current is applied, the lead plates immersed in the solution, the sulfate moves towards the anode. It's just very simple. Sulfate is negative. The anode is positive. So the sulfate is attracted to the negative. Positive and negative attract. All right. The cation, which is the hydrogen ion in the solution, will be attracted to the negative electrode, the cathode. Okay, so it's just simple electrostatic attraction. At the cathode, when the hydrogen makes contact, the ion makes contact with the cathode, there are electrons available. And it will gain the electron, and it's going to form a bit of hydrogen gas. So that is why when you charge your car batteries, you've taken it out of the car, and you connect up the charger to it, it must be done in a well-ventilated area. Okay. In the olden days, the batteries had little plugs that you had to unscrew to open it up, otherwise it builds up gas. Nowadays, they have little valves in them to release the gas. Now, at the anode, the red one, the positive one, the sulfate ion, which is negative, gives its electrons to the anode. It loses the electrons. Electrons can't dissolve, so it will move into the circuit. Okay? So it gives its electrons to the anode and reacts with water to form sulfuric acid and oxygen atom. The oxygen atoms produced reacts with the lead, and it forms lead oxide. There's a typo. The 2 must go down there. All right. So when it's charged, the one electrode is actually covered with lead oxide. Now the lead acid cell can produce electricity. It has been charged. When it discharges, we find that at the anode we have the lead oxide, and at the cathode it's simply lead. If you read it up in the text, they talk about sponge lead. It's just, it looks like a sponge because it's like bubbly. It's filled with bubbles. It's just to increase the surface area on which the reaction occurs. Now, during the process of discharge, the current, remember now, it's going to supply electricity to a light bulb, for example, or the radio. Okay. The current within the cell is moving from within the cell, from the cathode to the anode. They say the hydrogen ions will move to the anode, the sulfate ions to the cathode. At the anode, the hydrogen combines with the lead peroxide and it reacts to form sulfuric acid, with the sulfuric acid to form lead sulfate. At the cathode, the lead and the sulfate, they combine and they also form lead sulfate. So during the discharging of a lead acid battery, when you use it, all right, the plates of the cells are both converted into lead sulfate, which is whitish in color. All right. Unfortunately, this continuous recharging cycle of car batteries, they've got a lifetime of about 2 years. They've been designed to last that long. After that, you have to throw it away and buy a new one. All right.
Ladies and gentlemen, are you ready for your July showstoppers?
Yes. What you want to do?
It's showtime.
Who's he? The prince of our clan.
Hold on tight because we're about to seize every moment.
The world is not a playground. It's a battlefield.
These showstoppers are in it for the long haul.
Really?
GoTV's here to shower you with amazing shows.
You're somebody or you're nobody.
We are Unstoppable Madness. GoTV. Live it, love it.
Share with us on #LearnOn1. Tell us what you're learning and where you're learning it from. Send us your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better.
This story, there's something else going on.
Have you ever seen someone die in front of you?
Once.
School teacher, he's a local family man.
That's what he wants everybody to believe.
Death isn't going away. It's getting closer.
Follow Detective Harry Ambrose as he uncovers the most disturbing case of his career in the third installment of The Sinner. If you're itching for more serial entertainment, then tune into Bull and discover the science behind winning a case. Or delve into the twisted world of Isono, a brand new African telenovela. And live large with Don Cheadle as he builds a Wall Street empire in Black Monday. Only the best series right here on
We have finished up with the reduction oxidation reactions. And the next thing then that we must have a look at is the electrolysis. Now, electrolysis, both for higher and ordinary level, the basics.